Everyone, my name is Joe Nino Rapa, and today I'm going to share with you the findings from my experimental study on obstacle detection using sound signals to detect the state of a door, whether it's open or closed. This study is part of my work in data acquisition course and explores whether sound characteristics can be used as reliable indicators for detecting environmental changes, such as determining the status of a door or if it's open or closed. By the end of this presentation, I hope that you will have some understanding of sound transmission principles and perhaps how it can be applied in real-world scenarios, such as smart home technologies, security solutions, and automated detection technologies. The main objective of this study was to explore whether the state of a door could be accurately determined by analyzing the sound signals that passes through or around it. To achieve this, we conducted the analysis in two domains. The first is the time domain, where we monitor changes in amplitude over time, and the second is the frequency domain, where we break the signal down into its constituent frequencies and observe how the energy is distributed across them. For this experiment, we used three types of sound signals: the pure sine wave tones, human speech or voice, and a musical track. These were played in scenarios where the door was both open and closed. By measuring variations in the energy and frequency components of the signals under these two conditions, I hope to answer the questions: can the door state be reliably inferred from these acoustic principles or properties? And I bet that the preliminary findings were very promising. I have observed that lower frequencies, particularly those in the range of 100 to 200 Hz, remained relatively unaltered when the door was open. However, these frequencies experienced significant attenuation when the door was closed. On the other hand, higher frequencies, such as those around 500 Hz, were more heavily suppressed when the door was closed. Here's the experimental process which I have used in my work. First is the generation of the audio tones. I use Python to generate pure sine wave tones, and this allowed precise control over the frequencies being played and analyze how the door impacted them. The second is the reading and the preparation of the files. The recorded sound signals were processed and prepared for further analysis in both time and frequency domains. Third is the playing and the recording of the signals. I played the audio tones through a speaker and recorded the sound using a microphone, both when the door was open and when it was closed. This helped us understand how much of the sound was blocked or absorbed by the door. Fourth is the plotting and the comparing of the signals. This step was to plot the recorded signals and compare the differences between the open and closed door conditions. And then we go to the repetition of the experiment to validate that our data was reliable, and several experiment times was done to eliminate the effects of random variations. Six is the estimation of accuracy. I assess the accuracy of the system based on the multiple measurements collected, checking for consistency and how the door state could be detected. Seven is a testing with speech and music. To further validate the results, I tested the system with more complex signals such as human speech and a musical track to see if the same trend held true across different types of audio input. Eighth is to validate the results. Finally, I validated the results and compiled them into a report, making sure that the conclusions are the findings and the discussions and the results were supported by consistent data. The experimental setup was carefully designed to capture the sound signals in both open and closed door conditions. I simply placed a speaker on one side of the door and a microphone on the other end, ensuring about 1 meter of distance between them. And when the door was open, the sound was able to travel freely from the speaker to the microphone with minimal interference. However, when the door was closed, apparently it's black or reflected a significant portion of the sound waves. This created a noticeable difference in how much sound energy reached the microphone, and particularly at higher frequencies, which are more easier blocked by solid objects. The room was kept as quiet as possible to minimize any background noise or interference that could affect the results. In the time domain analysis, I focus on how the amplitude of the sound signals changed over time. This provided a clear picture of how much the signal was weakened by the door. When the door was opened, the amplitude remained strong as the sound traveled and abstracted from the speaker to the microphone. However, when the door was closed, the amplitude dropped significantly, indicating that a portion of the sound had been either reflected back or absorbed by the door. This observation is crucial because it shows how door directly impacts the intensity of the sound that passes through it. In the frequency domain, I applied the fast Fourier transform, or FFT, to convert the recorded signals from the time domain into the frequency domain. This allowed us to observe how the door affected the sound at various frequencies. The results revealed that higher frequencies were more affected by the door, experiencing significant attenuation. Lower frequencies, however, particularly those below 500 Hz, were less impacted and passed through the door with less reduction in energy. This confirmed that what we have expected, that higher frequencies are more easier blocked by barriers like doors, while lower frequencies can diffract or pass through more effectively. The results of the experiment showed that sine wave tones in the range of 100 to 200 Hz experienced the greatest difference in attenuation, with a value of about negative 13 decibels when the door was closed. This indicates that low frequency tones are particularly sensitive to the presence of the closed door. In contrast, speech and music signals, which contain a wider range of frequencies and more complex harmonic structures, exhibited lower attenuation values of around negative 7, 101 decibels to around negative 7.98 decibels respectively. These results suggest that low frequency tones provide a clearer and more consistent reduction in energy when a door is closed, making them effective in detecting the door status. The two sample t-tests which I have conducted confirm that these frequencies or these differences in the frequencies in energy between open and closed conditions were statistically significant, providing strong evidence that sound signals can be used to detect whether the door is open and closed. That concludes my presentation. Thank you for your attention. Your feedback is greatly appreciated.